All right, good evening and welcome to today's class, lecture 5 on static magnetic fields. And as I said, having had a look at static electric fields, it is well that we continue with static magnetic fields since we are looking at electromagnetic fields. So what creates a static magnetic field? But of course, one of the ways that a magnetic field can be created is from a permanent magnet. If you have a magnet, this magnet, because it is magnetized, will create a field around it. And any objects within the field of the magnet, if it's a magnetic material, it can be attracted to the magnet. Or if you bring another magnet, depending on the alignment, this magnet will attract that other magnet. So the attraction is possible or repulsion is possible because there's a field around the permanent magnet. So when you have a permanent magnet, you can create a magnetic field. That magnetic field will be static. It will be a static magnetic field, not a dynamic one. Also, when you have a moving charge, if a charge is accelerated, the acceleration of that charge also creates a magnetic field. So that's the second way a magnetic field can be created. The third way, which is a current flow, is actually very similar to that of a moving charge because electrons moving is what constitutes a current flow. So these are the ways by which a magnetic field can be created. When was magnetism discovered? It was discovered when a piece of magnetic lodestone were found to exhibit a mysterious attractive power. So this stone or lodestone was seen to be able to attract pieces of metallic materials. And because this lodestone was found in an ancient Greek city called Magnesia, magnetic properties were associated with the lodestone. And so we have derived terms like magnet, magnetism, magnetization, etc. They became popular and they came to stay as a result of the experiences with the lodestone, which was found in a place called Magnesia in ancient Greek. Now, when a small test charge Q is placed in an electric field, so you have an electric field which is created by some other charge, let's say positive charge, that creates an electric field like this. Static electric field. And then you place a charge Q in this field. This charge will experience the force of the field or the electric force of the field. That force is given by QE, where E is electric field intensity. Now, assuming this charge, as a result of this force, this charge is moving because when the force is exerted, the force of the field, E, is exerted on the charge will move. If this charge is moving and it happens to move through a magnetic field, so first the charge is moving under the influence of the electric field. If the movement of the charge passes through, or if the charge moves and then passes through a magnetic field, which has a magnetic flux density B, then there's also a magnetic force that will be acting on the charge. This magnetic force, Fm, is given by the product of the charge its speed, which is a vector, cross B. And B is the magnetic flux density. This cross is not the same thing as what? Times. Cross is different from times. When you have A cross B, the result is what? The magnitude of A times the magnitude of B times sine of the angle between them. That is a definition for A cross B. And then when you have the angle between them. So U cross B is not the same thing as U times B. And this U is the speed with which the charge is moving. So the magnetic force on the charge is given by Q times U cross B. And as I said before, U is the velocity of the moving charge. And B, which is the magnetic flux density, is measured in watts Webers per meter square or Tesla. So you can then understand that the total field that is acting on the charge, the total force that is acting on the charge F is a result of the electric force plus the magnetic force. So these two forces are acting on it. And if you remember, the electric force F, which is Fe, is given by what? Q times the electric field intensity. And the magnetic force Fm is Q U cross B. In that case, the total or the sum of the force acting on the charge will be QE for the electric plus QU cross B. So now we can factor out Q, and then we have Q into brackets E plus U cross B. So Q should be in brackets. And that is the total force acting on the charge. And this total force is as a result of the electric force and the magnetic force. Now this equation here is called the Lorentz force equation, And it's one of the fundamental postulates of the electromagnetic model, which means that it cannot be derived from other postulates. So it's a fundamental postulate. But as we did with the case of the electric field, we can express the fundamental postulate from our understanding of the behavior of the phenomenon of magnetic field. So in the case of electric field, we specify the divergence of the electric field. And we say the divergence of E was equal to what? Rho over epsilon naught. This is rho v over epsilon naught. And then we also specify the curl. And we see curl of E for static electric field is equal to 0. So that the static electric field is irrotational, and the divergence will depend on the volume charge density and inversely depends on the permittivity of free space. So similarly, we can have fundamental postulates for the magnetic field. We shall discuss it further. Now, because the magnetic field is divergenceless, it doesn't diverge, we say that it is solenoidal. It is solenoidal. In the case of the electric field intensity, we saw that curl of E equals 0, and the curl of E equals 0 means it is what? Irrotational. Okay? But in the case of the magnetic field, the curl of B is not 0. The curl of B is given as what? Mu naught times J. Mu naught is the permeability of free space. The permeability of free space. And then J is a current density. J here is a current density. Let's try to understand the fundamental postulate also. why is the divergence of the magnetic field equals 0? In other words, why is it divergenless, or why is it solenoidal? If you look at the case of a bar magnet, like this, a bar of magnets, okay? This is the way the field is. So you can see that the field will originate from the North Pole, and then it will come to the South Pole, pass through the magnet, and then continues the same way in either direction. So you can see that the field closes upon itself, goes and closes upon itself. It doesn't diverge outwardly like we had in the case of the electric field. In the case of the magnetic field, the field closes upon itself. It does not diverge, which is what explains the fact that the divergence is equal to what? 0. What about its rotation? What will determine the rotation? Now, in the case where we are considering the field created by a current, we said the field can be created by a permanent magnet or a current. If we take the case of a field created by a current, let's say this is the conductor in which a current is moving through. The density of the current is J. Now, this conductor which is carrying a current, a time-varying current, will create a magnetic field around the conductor like that. You see, so even in the case of the current carrying conductor, the magnetic field that is forced or that is formed is also closes upon itself. It closes upon itself, but it has some rotation. And that rotation will depend on the strength of the current density as well as the space in which the field is created. And that space which the field is created is free space. It is characterized by mu naught, which is the permeability of free space. Please, unlike yesterday, it just dawned on me, if you have any question at any point, unmute your mic and ask the question before we even continue. Yesterday, I think we had this class from beginning to the end without anybody interrupting with any questions. Please, at any point, you can interrupt with a question and then we'll address it. So, the two fundamental postulates. Is there a question? The two fundamental postulates for the magnetic fields are one that specifies the divergence and one that specifies the curl. The divergence is 0 because the field does not diverge. Therefore, it is solenoidal. As for the rotation, it has a rotation, and the rotation of the field will depend on the strength of the current density that is creating the field, as well as the medium through which the field is created. So again, J is the current density, which is measured in amperes per meter square. Now, just as we did with the electric field, we can do the same thing with the magnetic field. We said that the divergence of the magnetic field is 0, right? And what did we do previously? We take a volume integral of the divergence. So divergence of B, take a volume integral, dV is equal to 0. And the divergence theorem, as we said before, allows us to convert this volume integral into a surface integral. And the surface integral will be integral S B ds is equal to 0. So that the totality of the field in terms of its outward flow is 0. There is no outward flow. Now, this is very instructive. Compare this equation, integral S ds equals 0, with its counterpart in terms of the electric field. That is integral d ds is equal to Q. If you remember that, what we saw yesterday. So we have integral S B ds is equal to 0, and then integral S d ds equals what? Q. D here is the electric flux density, and B here is the magnetic flux density. Yes. Question?
Please, the electric one.
Okay.
Yes, please. Is it was it D?
Your network is very poor. If you can type in the
equal to rho S or Q.
I cannot hear what you said because your network is very bad. Maybe if you have video on, you can turn on the video. Sorry? There's also, you can also type a message. If I can read the message, then I can answer. Okay. Or if your network becomes better, then you can ask the question again. Okay. So compare these two equations.
Yeah, I was.
I've lost you again.
Yeah, I was asking about the equation for the electric one.
Yeah.
Okay, let me see.
Yeah, I can hear you. So go ahead. I can hear you. I can hear you. Go ahead.
The equation for the electric.
What is wrong with it? We previously stated the equation for the electric field.
Let's continue. It seems my net is no good.
Okay, I think I can get
I'm trying to see whether
I can get the question. Listen, previously the electric field, we looked at it in terms of the electric field intensity. And we said that...
Yes. Okay. Equation for the electric field yesterday. The one with the S to rho S or Q. Yeah, you wrote
integral ds equals what? It was equal to integral rho s ds, right? And this rho s ds is equal to Q, because rho s, the surface charge density is Q divided by the surface area S. Okay, so let's say we're dealing with a small area ds. So Q then will be equal to what? Rho s ds. Sorry. Rho s ds.
Yes, sir.
And if you want the total field to integrate rho s ds, it will be equal to Q. Do you see that?
Okay.
Do you follow? Okay. So let's go back to the two equations. We have integral S B ds equals 0. For the electric field, it's integral S d ds equals what? Q.
Yes, sir.
Okay. Now you see that.
Yes, sir. Yes, sir.
Okay. Now you see, for the case of the magnetic field, it's equal to 0.
Yes,
but for the case of the electric field, it's equal to Q. So in this case, we say, for example, that there is no magnetic analog for the electric charge. Because if there was a magnetic analog, then integral B ds should be equal to some magnetic charge. But there is nothing like a magnetic charge. So in the case of the magnetic field, this is 0, but in the case of the electric field, this is Q. It tells us that there is no magnetic analog of the electric charge. So there is not, the magnetic field doesn't have something that you compare directly to the electric charge. Even though a bar of magnets has north and south pole. The north and south pole do not equate to a positive charge and a negative charge. And you will understand why. So we cannot isolate a single magnetic charge. That doesn't exist. Because whereas in this case it's equal to Q, in this case here it is equal to 0. So we conclude that there is no magnetic analog for electric charge, which means that there are no magnetic flow sources. Remember, the charge Q for the electric field is the source of all electric field. As I said before in the example that I gave for the magnetic field, the force or the flux lines always what? Close upon themselves. Or if you look at a conductor, the flux lines always close upon themselves. And therefore, there's no magnetic analog for the electric charge. As in the case of the electric charge, for example, when you have a positive charge, you can see that there's a flow of the field outwardly because there's a source and therefore there's a flow outward. But because the magnetic field doesn't have an equivalent to this, it doesn't behave as such. So the magnetic flux lines always close upon themselves, as we demonstrated. And there is no magnetic flow sources and there is no magnetic analog for electric charge. So if you take, still looking at this equation, if you take a bar of magnets, it has north and south pole. If you break this magnet into two, you still have north and south pole here, and then north and south pole here. No matter how often you break it, you cannot isolate a single north pole or isolate a single south pole. Anytime you break the magnet, you still have a north pole and a south pole. Therefore, magnetic pole cannot be isolated into separate north and south poles as in positive and negative charge, reinforcing the fact that there is no magnetic analog for the electric charge. So this is a clear diagram that demonstrates that the magnetic flux lines, they follow a close path from one end of a magnet to the other end outside the magnet, and then continue inside the magnet back to the first end. That's what you see here. So they start like this, and they continue inside the magnet, then outward again, and they continue inside the magnet, then outward again, and then they continue inside the magnet, and that's how the flux lines are formed. So how are we able to designate a north and south pole? Because when the magnet is suspended, it will seek the Earth's north and south magnetic poles, and therefore every bar of magnet will have a north pole and the south pole in accordance with their seeking of the Earth's magnetic field. Now we looked at the divergence equation, and then we came to integral B ds is equal to 0. That is from divergence of B equals 0. Then we can also look at the curl equation. For the curl equation, curl of B is equal to what? Mu naught times J. And then you can integrate this as well. If you integrate, then integral curl of B. Remember, the rotation will occur on a surface. Therefore, the integral is what? A surface integral. Will be equal to mu naught is a constant, and integral J ds. Now we talk about the current density. If you take a conductor and you take any cross section of the conductor, what you're looking at the cross section is a surface, and the current that is passing through the cross section is a surface current, which is Js. And therefore, in accordance with the Stokes theorem, we can convert this surface integral to a line integral, and that becomes what? Integral B dl will be equal to, and since J, the surface current will be equal to the current itself divided by the surface, then integral Js ds will be equal to what? I will be equal to J times S, and therefore this will be equal to mu naught times I. Integral C B dl will be equal to mu naught I, where I is the current, not the current density, that is flowing through the conductor. And this equation is the form of what? Ampere's circuital law. Ampere's circuital law, which says that the circulation of the magnetic flux density in a non-magnetic medium around any closed path is equal to mu naught times the total current flowing through the surface bounded by the path. Mu naught times the total current flowing through the surface bounded by the path. What is the bounding by the path? If you have a conductor which is cylindrical in nature, the cylindrical nature of the conductor is the bound between which the current flows. And that is what is meant by a surface bounded by the path. And that path around the surface of the conductor is this closed path, which is indicated as integral C in integral sign. So Ampere's circuital law is this, and it says that the circulation of the magnetic flux density in a non-magnetic medium around any closed path is equal to mu naught times the total current flowing through the surface bounded by the path. So when is Ampere's circuital law useful? It is useful in determining the magnetic flux density B caused by a current I. What does that mean? It means that if you know the current I, and you want to find the magnetic flux that is caused by the current I, you use Ampere's circuital law, because integral B dl equals what? Mu naught I. And since you know I, and mu naught is constant, it should be possible to find B from this law. So in summary, the fundamental postulates are this. The differential form, divergence of B is 0, curl of B is mu naught J. And then in the integral form, the cyclic integral of B ds equals 0, and for this one equals mu naught I, which is a statement of the Ampere's circuital law. So let's look at an example to solve some of these problems, or to illustrate this problem. So we have an infinitely long, straight, solid, non-magnetic conductor. So we're talking about a conductor that is infinitely long, with a circular cross-section of radius B, carries a steady current I. Determine the magnetic flux density both inside and outside the conductor. This problem is similar to the problem we looked at for the case of the static electric field. There are various regions to be considered. And then for the various regions, there is some amount of current that would flow through it. And therefore, the application of Ampere's circuital law should help us determine the magnetic field. So this is an illustration of the conductor. The shaded part here is a conductor. So you imagine a thick conductor which has a radius R1. R1 is the radius of the conductor. Sorry, the radius of the conductor is what? B. That's the radius of the conductor here is B. That's the radius of the conductor. Now, if you want to consider the magnetic flux density, which is inside the conductor, so let's take a section like this inside the conductor. That section will have a radius we assume to be what? R1. This radius here, R1. Now we should understand that it's not all of the current that will flow in this small section here, because there's still some of the current flowing here all the way to the edge of the conductor. So the current that will flow within the radius R is a fraction of the total current. So that fraction is according to the surface area. The surface area for the radius R1 is pi R1 squared. And for the surface B, that's the total volume or the total surface of the conductor is pi B squared. So you have pi R1 squared and pi B squared. So what is the ratio of the current that flows in this area? It will be pi R1 squared divided by pi B squared times the total current I. And since pi is common, this is equal to R1 over B all squared times I. And therefore, when we apply Ampere's law to this section of the conductor, we will not see that integral B dl is equal to mu naught I. Why? Because it's not the total current I that is flowing within that section. But we can write that integral B dl is equal to the fraction R1 over B all squared times what? I left out the mu naught times mu naught also. So this would be the way to express it. And therefore, from this, we can find what? B. So for that section, integral B dl is equal to mu naught times R1 over B all squared times I. And this dl can be found from what? R1 d phi. If this angle is phi, what is the length here? The length of the radius. The length of the arc subtended. That arc will be what? R1 d phi, because the phi will be equal to R1 will be equal to the arc. The phi will be equal to the suspended arc, let's call that L, divided by R1. Usually, when you find what do you call it? The tan of an angle, tan theta is what? Opposite over what? Hypotenuse. And so if you take an angle here, small angle, the theta, tan of the theta must be equal to the opposite. And that opposite will be what? The arc here, which is subtended, let's call that L. And the hypotenuse will be what? R. But for a very small angle, tan of the theta is the same thing as the theta. And therefore, the theta is equal to L over what? R1. Or L is equal to R. Phi, R1 d phi. And that is equal to the fraction of the current as we indicated. Now, if you integrate this one, B is the flux density, pull it out, and then R1 is also not dependent on phi. Then you have integral the phi will be equal to mu naught R1 over B all squared times I. If you integrate the phi, you get phi. So that's phi. And that is between what? 0 to 2 pi for the entire circle. So 0 to 2 pi will give you what? If you put 2 pi, you have 2 pi. If you put 0 to 0. So integral of the phi is what? 2 pi. And therefore, if you integrate this one, then you have B here. That is B, phi 1. Then you have R1 integral d phi will give you what? 2 pi. 2 pi. So that is why you have 2 pi r1 b phi 1 is equal to mu naught r1 over b all squared. And from this, we can find an expression for b by dividing 2 pi r1 by this. So r1 here is squared. If you divide by r1, it becomes r1. And then we already have 2 pi here, and that comes here, and then the b squared. And so this becomes the solution for B, the flux density inside the conductor. But when we come to consider outside the conductor, then we can use all of the current. We don't need a fraction of the current. And that is the next part of the question. So for B2, that is outside, then integral B dl equals what? Sorry. Integral B dl equals mu naught I, all of the current, not a fraction. Sorry, this is the previous one. Yeah, so integral B to dl equals mu naught I. And as we've seen before, integral B R2 d phi will be what? 2 pi R2 b phi. And therefore, b phi will be equal to what? If you divide both sides by 2 pi R2, then you have mu naught I over R2. And that is how you find the magnetic flux density outside the conductor. Is that okay? Vector magnetic potential, I will skip this and just state the results. Now, this A here is called the vector magnetic potential. The derivation is simple, but I'll just skip it for the purpose of clarity. So we come to this equation here, which says that the gradient squared of A equals minus mu naught J. We know that J is what? The current density. A is the vector magnetic potential here. Now, this is called a vector Poisson's equation. Anytime you see del squared, a certain vector, whatever vector, is equal to something else, y whatever, that is called what? A vector Poisson's equation. So this vector Poisson's equation will have a solution. And even though we didn't say it, this equation here, which was for the electric potential due to the volume charge density rho v, which we saw yesterday, is actually the solution to another vector magnetic potential, this. So this is an example of a Poisson's equation. And this Poisson's equation, we said the solution for this Poisson's equation, we saw the solution, but we didn't know from which equation it came from. It's 1 over 4 pi epsilon naught, then integral rho v over r squared dv. That is the solution that we quoted for the electric potential due to a volume charge density. And therefore, for the Poisson's equation, del squared A for the vector magnetic potential equals minus mu naught J. We can write a similar solution for it. In this case, it becomes mu naught divided by 4 pi integral J. Instead of rho v, we have what? J here. So integral J divided by R, I think it's R squared dV. So because here, if you look at these equations, for the case of the electric field one, the epsilon naught is down. But for the case of the vector magnetic potential, the epsilon naught is a numerator. So here epsilon naught is down, but in the case of vector magnetic potential, epsilon naught, sorry, mu naught is a numerator. It's a numerator here. So mu naught comes as a numerator. So in the solution of del squared V equals rho V over epsilon naught. So epsilon naught here is dividing because it's already a denominator here. In the case of the vector magnetic potential, mu naught is a numerator. Therefore, it has to come on top. And that is why in this solution here, you have mu naught on top divided by 4 pi and j over r squared dv. This is necessary for future discussion when we discuss Maxwell's equation and Biot-Savart law. So I will not bore you with the derivation for the Biot-Savart law. I will just quote it and then discuss how it can be used. So this here is the Biot-Savart law, which relates the magnetic flux intensity, the magnetic flux density, to the current that is flowing through a conductor. And the L here is the L that we have always seen, and R squared is the distance to the point of observation. This equation here is called the Biot-Savart law, and it helps determine B, which is caused by a current I. So where it is not possible to apply the Ampere's equation, the Ampere's law, integral B dl equals mu naught I, then we can apply this Biot-Savart law in order to find B from a certain current I. Okay, so the Biot-Savart law here is where we conclude the discussion. We'll have part 2 of this magnetic field or static magnetic field. So if at the moment there are some questions to address, we can look at them. As I said at the beginning, there are some things that are very peculiar to telecom because there are future courses that you require to know some of these things. But given that you're an electrical engineering student, it suffices to know that this is the Biot-Savart law and that it can be applied to find B when I is given from a particular point of observation. We don't need to go through the derivation as we did yesterday. So any questions?